Okay, welcome to 1.07. Today we're going to jump into what a complex number is and perform operations with complex numbers. So the first part of a complex number, in fact the part that we haven't discussed yet, there are two parts. The part that we haven't discussed yet is what's called an imaginary number. And so we want to define that. We saw an example of it yesterday, and I briefly talked about how an imaginary number is the square root of any negative number. And to give you a little bit of history, when mathematicians were trying to solve quadratic equations, they ran into this situation where they had the square root of a negative number. And since all of the real numbers that they had used didn't work, they had to come up with something that was different than a quote-unquote real number. And so what's different than something that's real is something that's imaginary, right? An imaginary number doesn't have any real-world meaning. A real number has real-world meaning, right? Positive 1, negative 1.2. Those numbers mean something in a real-world context. An imaginary number is just that. It's imaginary. And it's used to define the square root of any negative number. And so just like in the real number system, we have the number 1, which we can kind of use to count up to any number, if you will, any whole number. The imaginary numbers also have what's called an imaginary unit, which is it's the imaginary numbers version of the number 1. And so the imaginary unit is what's called I. It's written as a lowercase I. And the definition of I is the square root of negative 1. So the square root of any negative number is called an imaginary number and can be written in terms of I, just like any real number can be written in terms of 1, right? 11 is 11 times 1, right? 12.5 is 12.5 times 1, right? And so what we can do is we can write any negative square root of a negative number in terms of i's. And so let's go ahead and do an example for how to do that. So go ahead and pause the video, make sure you have your definition written down, and then I want you to try each of these examples, and then go ahead and press play, and we'll talk about it. Okay, so first what we want to do is we want to write the square root of negative 9 in terms of I. Now, think about what you would do to write the number 9, the real number 9, in terms of 1. Well, you would write 9 times 1, okay? And essentially, what we're going to end up with is the same idea here, except instead of using 1 in the real numbers, we use I in the imaginary numbers, and this is an imaginary number. So let's talk about how we can do this. If you have the square root of negative 9, we're going to use the property of square roots to kind of break up the part that we can represent in real numbers and the part that is just an imaginary number I. Okay, so let's rewrite this as the square root of 9 times negative 1. Okay, now the property of square root says that if you're multiplying two things inside the square root, or any number of things for that matter, what you can do is you can take the square root first, so take the square root of 9, and multiply that by the square root of negative 1. And you can check that, right? Imagine you did the square root of 9 times 4. Go ahead and try that out on your own, and you'll see that you end up getting 6 either way you do it. And so now, think about each part. First, I have the square root of 9. We know what real number that is, right? That's the number 3. And then you have the square root of negative 1, and that is the imaginary unit I. So how many i's do you have here? Well, you have 3 times I, or 3i. Now, with this in mind, go ahead and try example number 2 on your own again. I bet you can get it this time. All right. So the square root of any negative number, and I just want to be really clear on how you write the square root of any negative number. So I have square root of negative n. Now that means that n has to be greater than 0, because if you had a negative times another negative, it would be a positive. So to write a negative number, I'm saying let me take a negative and multiply it by any positive number n. That gives me the negative version of that number. So in the same way, what I want to do is take the square root of negative n, and I want to represent it in terms of my imaginary unit I. Okay, so we can follow the same idea here. We can split this up so that we have the square root of n times negative 1. And now I can split them up. Now I can split them up outside, so I can break up the square root, if you will. And what that allows me to do is write the square root of n times the square root of negative 1. Now, here I've got to be a little careful. N can be any number, that's so long as it's positive. So it could be 3.2, it could be 27,000,000.6. It might be a number where we don't know the perfect square of that number. It doesn't work out to be 4 or 3 or whatever. So we just leave it as whatever the square root of n is. If you have a calculator, you can compute this easily. But we'll just leave it as whatever the square root of n is. And the square root of negative 1 is, of course, I. So any square root of a negative number is an imaginary number and can be written in terms of the square root of the positive version of that number times I, or the imaginary unit. Now, to further investigate this, what we're going to do is we're going to add on to our definition of the imaginary unit. Okay? And to do this, there's the way that we have defined it here, that I is the square root of negative 1, is just one way to define it. In fact, there's an equally accurate way of defining this that you can get by just squaring both sides. And I think you'll. So what I'm going to do is I'm going to rewrite this, but I'm going to square both sides. So let's come over here. So if I have this I and I'm squaring it, that's I squared. And what will that be equal to? Well, off to the side, let's think about what happens if you take the square root of negative 1 and you square it. Well, maybe try this out with a slightly easier to work with number. Try the square root of 4 squared. Well, the square root of 4 squared is just 4, right? Square root of 4 is 2, squared is 4. And we see that the square root and the square, they're inverse operations, so what I'm left with is just negative 1. Okay? Well, that's kind of interesting, right? So that the value of I squared is actually negative 1. And so both of these ways of defining I are equally valuable and equally correct. In general, I like to stick with this one. It helps me think of the imaginary unit just as it is, an imaginary unit. But it's also equally accurate to say that I squared is equal to negative 1. It means the exact same thing, just with a little algebraic manipulation. So what we're going to do now is we're going to further define what a complex number is by combining the idea of an imaginary number and a real number. All right, the moment we've been waiting for now, the definition of a complex number, and as you might have guessed, it includes imaginary numbers and something else, which makes it complex. So a complex number is any number of the form a plus b times I, where a and b are real numbers, just regular old real numbers, and I is the imaginary unit. And I wrote the definition here. I is equal to the square root of negative 1, or another way of writing that is I squared equals negative 1. And as you might have imagined, this complex number seems familiar. Where does it seem like we've seen what could look like this? Well, if you think back to finding the roots of a quadratic function, we remember that we had a square root of a negative number pop up. And a square root of a negative number can be written in terms of I. So while we have that square root of a negative number, that imaginary part, there's also a real part. And this actually corresponds to the negative b over 2a portion of our quadratic formula. And so what we'll end up with is now a complex number. That's what it's called. It has a real component and an imaginary component. So this is an important thing to remember as well. Sometimes what we call the real component we abbreviate RE, okay, real, and the real component is the A value. The imaginary component, and this is where it gets a little bit tricky, the imaginary component is the value of B. And you might be saying, what do you mean B? B is a real number. Yes. The imaginary component, or sometimes it's called imaginary part, it's abbreviated IM, is the B value, because the B value is always multiplied by I, meaning it is an imaginary component. And so we can talk about the real part of a complex number and the imaginary part of a complex number. Okay, so with that in mind, let's take a look at a couple of examples. 3 plus 5i. So here, the real part is 3. The imaginary part is 5. Think carefully about this here. Is there any way that I can simplify this? Can I, for example, add 3 and 5i? The answer is no, right? This is a real number. This is an imaginary number. And the two are in totally different worlds, right? One makes sense in the real world, and one is just an imaginary way that we define the square root of negative numbers. And so this is as simplified as we can get this function, because we can never combine a real and an imaginary number with addition or subtraction. Okay? Here's another example. In this case, the real part is 5, and the imaginary part, be careful, is negative 2, because I am adding a negative value, making it minus 2i. So the way we read this is 5 minus 2i, or 3 plus 5i in that case. Another example, negative 3.14 plus 2.7i. The real part is negative 3.14, and the imaginary part is 2.7. Okay, so now what we want to do is consider what would happen if we took complex numbers and started adding, subtracting, multiplying, and dividing them. So before you move on to the next slide, pause the video for a second and think about what would happen if you took 3 plus 5i and added 2 plus 2i. And then, when you're ready, go ahead and move on to the next slide, and we'll discuss how to add, subtract, multiply, and divide. All right, let's start with adding and subtracting. Now, adding and subtracting are similar, and so what I'm going to do is I'm going to go over how you would add it, and then you can redo it with subtraction. So, adding and subtracting. What we want to think about here is what part of each of these complex numbers can be combined with another part. And what you'll notice here is that A and C are both real parts. So I can combine real parts because they're both real numbers. And B and D, these are imaginary parts. So if I have BI plus DI, I can combine those as well. So that's exactly what I do. The way that I write this is a new complex number where I've added the two real parts, A and C. So I have A plus C. This is my real part. Okay? And I've added them because I'm adding. Now, I then have an imaginary part. I can add those together as well. So I'll have A plus BI plus, and now the imaginary part, which I'll do in a different color, B plus DI. Now I have to be careful. How do I add BI's and DI's? Well, I just need to add B and D and then multiply by an I at the end. And so this will just be B plus D all times the imaginary unit I. Okay? And so this will work with subtraction as well, and I encourage you to go ahead and think about what it will be, and I will show you in just a second. Okay. As you might have guessed, subtraction is going to work exactly the same way, except instead of combining my real parts with addition, I'm going to find the difference of them with subtraction. And instead of combining B and D with addition, I'm going to take the difference of them with subtraction. So B minus D, A minus C, and I still write my complex number as A minus C, whatever that value is, plus, and notice the plus stays here, and that's because a complex number will just always add And if this value, b minus d, is a negative number, then this positive times a negative will turn into a negative. Okay? So let's go ahead and try a quick example to make sure we feel good about it. All right, we want to add this complex number and this complex number. Go ahead and pause the video, try this on your own, and then press play to see the solution and check your work. All right, so I first add the two real parts, so 3 plus negative 5, that's negative 2. Then I add the two imaginary parts, 6 plus negative 5 is positive 1. Notice that positive 1 times I is just I, so I'm left with negative 2 plus I. Now, I encourage you to try this if it were subtraction, okay? And if you do this in your head, if you think about what would happen with subtraction, we'd have 3 minus a negative 5. Minus times a minus would be a positive, so this would in turn be 8. And then we'd have 6 minus a negative 5, which would go positive, so we'd have 6 plus 5, which would be 11. And so I'd end up with 8 plus 11i. All right, now let's move into multiplying. Okay, so the basic idea is that we want to incorporate what we already know about multiplying two binomials. Binomial meaning it has by two different terms in it, by another binomial, which has two terms. And the method that we use to do this is foiling. And so we're going to FOIL this just as we would any regular binomial. And have faith in the process, and we'll see if it works out. So let's go ahead and get the first step down. I want you to try it on your own, and then go ahead and see what we get. Okay, so let's go through the first couple of steps here. First, a times c, get a times c, no big deal. Now, a times di. Well, notice this is just some number of i's, or imaginary units. And so if you have this number of imaginary units, and you multiply by a, you will have a times d i's. So a times d I, that many imaginary units. Same thing is true if I multiply c times bi, right? I have this many imaginary units, b of them, and I'm multiplying by c. So now I have c times b imaginary units. All right, so now we have bi times di. And here's where we need to make sure that we stay disciplined and trust the process. So if I multiply bi times di, first thing that I'll just write is that I have b times I times d times I. Now, notice that this is all multiplication. And so remind yourself that multiplication has a really cool property called the commutative property. The commutative property says that, for example, if you have, and I'll just write an example here. If you have 4 times 5, that's the same as 5 times 4. So it doesn't matter what order we multiply these in, so long as we multiply them all at some point. So let's rewrite this so that we have b times d times I times I. Okay, well, what's I times I? I times I is something times itself, so it's I squared. We still have b times d. Well, what's I squared? Go back to your definition and remind yourself that I squared is simply negative 1. And so this value here becomes b times d times negative 1, which is negative b times d. So over here, I have negative b times d. Okay, well, let's take a look at what we have. We have a times c. Those are both real numbers. So this is going to be a real number. We have a times d times I, so that's going to be an imaginary number. C times b times I, it's an imaginary number as well. And then b times d, negative b times d, that's going to be a real number since b and d are both just real numbers. So now we can collect like terms. These are both real numbers, so what we're left with is ac minus bd. That's the real part. The imaginary part, well, if I have a d i's plus c times b i's, let's just think about what that might look like. Imagine that a times d is 4, and c times b is 5. If you have 4 i's plus 5 i's, you have 9 i's. In other words, you're adding a times d and c times b, and that's the number of i's you'll have. So plus AD plus CB times I. And that is how you multiply complex numbers. I'll do one quick example for you, and then I'll let you go ahead and practice on your own. All right, here's an example. Try this on your own and see how far you can get. I bet you can get all the way. And then once you've given it a shot, go ahead and press play. Okay, there's a couple ways that you can do this. You can always FOIL it out, and if you FOIL it out, you'll end up with the right solution. But you can also take advantage of the fact that we FOILed it out already for any values A, B, C, and D. And so all we need to do is locate A, B, C, and D, and we can actually figure out what this will be. So notice our real part is going to be A times C, 2 times 3, which is 6, minus B times D, B which is 3, and D which is negative 4. So we have minus, and then 3 times negative 4, which is negative 12. That's our real part. Now our imaginary part is going to be A times D, 2 times negative 4, which is negative 8, plus C times B, which is 3 times 3, or 9, times I. So simplifying this out, we have 6 plus 12, which is 18, and then negative 8 plus 9, which is 1, so plus 1I, or just I. And there you go. All right, I'm going to put some problems for you to try. Here they are. You should evaluate each expression. You can evaluate each expression with what we've talked about. Each one should have a solution. Remember that squaring something is just multiplying it by itself. So go through, make sure you have an answer that is correct for each. It will allow you to be more successful in class.